Welcome to the A320 engines lesson. In this lesson, you will learn about the aircraft's two engines and their respective components and controls. In addition, we will review both normal and non-normal engine indications. Aircraft thrust is provided by two IAE V2500 series engines capable of producing up to 26,000 pounds or 117 kilonewtons of thrust. These high bypass ratio engines produce the majority of thrust through the fan section, resulting in high fuel efficiency and quiet operation. Each engine is managed by a full authority digital engine control, or FADEC. The FADECs take commands from the thrust levers, the flight management system, and engine master switches to produce the required amount of thrust. Controls and indications for the engines are located throughout the flight deck. Primary engine indications are displayed on the Engine and Warning Display, or EWD. Secondary engine indications are displayed on the Engine and Cruise pages. The IAE V2500 engine is a high-bypass dual-rotor axial flow turbofan. The main components of the engine are the fan section, a compressor section, the combustion chamber, the turbine section, and an accessory gearbox. To enable the Flight Management System, FMS, to provide accurate performance and fuel burn data, it is critical that the FMS uses the correct engine performance data. The MCDU's aircraft status page displays the aircraft model and engine type that is loaded in the performance database. The pilot checks this information against the flight plan during pre-flight on every flight to ensure it is correct. Each specific aircraft tail number is certified for only one engine airframe combination. The engine types are monitored by the FADEC. In the rare event that the incorrect engine or engines were installed and the FADEC programs do not match, an engine warning display caution message is displayed. The dual-rotor turbine engine consists of an N1 shaft and an N2 shaft, which are mechanically independent. The N1 rotor section is comprised of a fan and a 4-stage low-pressure compressor, which is driven by a 5-stage turbine. The N2 rotor consists of a 10-stage compressor driven by a 2-stage high-pressure turbine. Airflow is drawn into the engine by the N1 fan. The airflow entering the engines is split into bypass air and core air. The majority of the air flows outside the core, through the fan duct. This air provides the majority of engine thrust. The remaining airflow enters the core of the engine, where it is compressed by the N1 compressor. Downstream of the N1 compressor section, the core air is further compressed by the N2 compressor. 20 fuel nozzles inject fuel into the combustion chamber, where it is mixed with compressed air and ignited by two FADEC-controlled igniter plugs. After leaving the combustion chamber, the hot gases pass through the N2 and N1 turbines before being expelled through an exhaust nozzle. The N2 rotor is mechanically connected to a drive shaft which drives the accessory gearbox, located at the bottom of the fan case. The accessory gearbox drives many components including the engine oil pump, the engine fuel pumps, the engine fuel control unit, the FADEC alternator, the hydraulic pump, and the engine-driven integrated drive generator, or IDG. Each engine is equipped with its own independent full-authority digital engine control computer, or FADEC. FADECs are designed to maximize engine performance while providing for automated engine management and control. Each FADEC has two channels fully capable of operating the engine. If one FADEC channel fails, the other channel automatically takes control and operates that engine. Each FADEC receives thrust requirement signals from its Engine Interface Unit, or EIU, based on information provided from multiple aircraft systems, such as the LGCIUs, FMS, and ADIRS. Flight deck panel and control outputs to the FADEC are generated by the engine control panels, the thrust levers, and the MCDUs. Each FADEC uses fuel flow, engine acceleration and deceleration schedules, idle settings, and other inputs to control the engine and provide for maximum fuel efficiency. Functions of the FADEC include the following: automatic engine start, including automatic control, and sequencing of start valves, ignition, and fuel flow, automatic engine start interrupt, and adjustment of fuel flow and ignition when abnormal conditions exist, N1 and N2 overspeed protection in both forward and reverse thrust, and protection against EGT exceedance, only during automatic and manual starts on the ground. Other FADEC functions include automatic adjustment of minimum idle speed setting, both in flight and on the ground, calculation of maximum thrust values, thrust adjustment in response to commands sent by the autoflight system, adjustment of forward and reverse thrust in response to thrust lever position, while simultaneously limiting acceleration and deceleration schedules, regulation of reverse thrust sequencing, display of engine operating parameters via the ECAM, and detection, isolation, and recording of engine failures and presentation of that information to the engine warning display. The FADEC can be powered by the aircraft electrical system or by a dedicated engine-driven alternator. The status of FADEC power can be monitored on the EWD. When the FADEC is unpowered, amber X's are displayed. When powered, valid engine data is displayed. When the aircraft is first powered, the aircraft electrical system powers the FADEC for 5 minutes while the system performs a self-test. On completion of the test, electrical power is automatically disconnected. Power is reconnected just prior to an engine start when the engine mode selector is moved to Ignition Start. When engine rotation speed is sufficient, the FADEC power source is automatically switched from the aircraft's electrical system to the dedicated alternator. This alternator then powers the FADEC for as long as the engine is running. After normal engine shutdown, the FADEC power supply is automatically switched to the aircraft's electrical system for approximately 5 minutes and then disconnects. The FADECs use two modes of setting thrust, EPR and N1. EPR is the primary mode of thrust control. However, if a failure occurs and EPR mode is not available, the following occurs. Amber X's replace the EPR indications for the affected engine. The affected engine automatically reverts to N1 mode, and auto thrust is lost. The other engine should be manually selected to the N1 mode, allowing both engines to operate in the same thrust control mode. EPR indications for the unaffected engine are replaced with amber X's when its respective N1 mode push button is selected on. Two N1 thrust modes are available, rated and unrated. In the rated N1 mode, thrust lever position and thrust limit indications transfer from the EPR indicator to the N1 indicator. In addition, N1 mode limit indications, replace the EPR limit indications. In the unrated mode, thrust lever position and N1 limit indications are not displayed, and the FADEC overspeed protections are reduced. In addition, the N1 mode limit is not available, and amber X's are displayed below the N1 mode. Primary engine operating parameters are continuously displayed on the Engine and Warning Display, EWD. The EWD is normally presented on the upper ECAM and appears anytime AC power is established and the display units are turned on. The following information is provided on the EWD: EPR, EGT, N1, N2, fuel flow, thrust limit mode and its associated limit, and the flex temperature. Select the desired tab to review the primary engine indications. The engine page appears under the following conditions: whenever the engine push button on the ECAM control panel is selected, whenever an engine-related malfunction or exceedance occurs, or during engine start when the engine mode selector is rotated to either ignition start or crank. Secondary engine indications are displayed on the engine and cruise pages. Indications include fuel used, oil quantity, pressure, and temperature, N1 and N2 vibration, oil and fuel filter clogs. During engine starts, the start valve and igniter indications, and if an overheat occurs, the engine nacelle temperatures. Select the desired tab to review the secondary engine indications. The engine panel, located on the aft center pedestal, is used to control engine ignition and start functions. The selector has three positions: norm, ignition start, and crank. The selector is typically in the norm position. In this position, engine ignition is off unless it's automatically activated. In preparation for engine start, ignition start is selected. Both FADECs are automatically connected to the aircraft electrical system. This is indicated by the engine indications displaying on the EWD. Once both engines have been started, the selector is returned to the norm position. The engine page is removed from the system display. The crank position is used to rotate the engine without introducing fuel or ignition. Crank is used for removal of fuel vapors following a failed start on the ground and is commonly referred to as dry cranking the engine. With the engine mode selector at the ignition start position, moving an engine master switch to on initiates a start of the associated engine. During automatic starts, FADEC controls the opening and closing of the engine start valve, as well as the introduction of fuel and ignition. Once an engine is started, The engine master switch remains in the on position during engine operation. With an engine running, placing the engine master switch to off closes two fuel shutoff valves and provides a direct means of shutting down an engine. Located on the center pedestal below their respective engine master switches are the fire fault lights. The red fire light illuminates when a fire has been detected in that engine. The amber fault light illuminates if an automatic engine start is aborted, or a disagreement exists between the actual position of the high-pressure fuel valve and its commanded position. The engine manual start push buttons on the overhead panel control the engine start valves manually. When the engine mode selector is in the ignition start position, selecting an engine manual start push button on opens the start valve. Then, by placing the engine master switch to on, ignition and fuel are simultaneously introduced. The engine start valve closes when N2 reaches 43%. The engine manual start push button remains on until selected off, at which time the light extinguishes. When the engine mode selector is in the crank position, selecting an engine manual start push button to on opens the start valve, enabling dry cranking of the engine. When the engine manual start push button is then selected to off, the engine start valve closes and dry cranking ceases. Unlike traditional thrust levers, the Airbus thrust levers have no mechanical linkage to the engine. The thrust levers send electronic positional data to the FADEC. Without mechanical control, the Airbus thrust levers never automatically move. They must always be positioned manually. Located on either side of the thrust levers are the auto thrust instinctive disconnect push buttons, used to disconnect the auto thrust system. With auto thrust off, engine thrust corresponds directly to the position of the thrust levers in the same way as traditional thrust levers. Each thrust lever also has a reverser latching lever, which is manually raised to move the lever aft of the idle thrust position for reverse thrust application. The thrust levers are equipped with 3 stops and 3 detents. Idle thrust is selected when the thrust levers are positioned aft against the idle stop. Climb thrust is selected with the thrust levers in the climb detent. The next detent, Flex MCT, provides for 2 separate functions. During takeoff, Flex produces a reduced power takeoff. Once selected for takeoff, Flex thrust continues until the thrust levers are moved out of this detent. If the thrust levers are placed in the Flex MCT detent while airborne, Maximum Continuous Thrust, or MCT, is selected. Maximum thrust, referred to as takeoff go-around or toga thrust, is selected whenever the thrust levers are moved to the full forward stop. Reverser latching levers are located on the front of the thrust levers for control of reverse thrust. With the thrust levers positioned in the idle stop, raising the reverse latching levers and moving them aft places the thrust levers in the reverse idle detent. Maximum reverse thrust is commanded at the maximum reverse stop. The engine's oil system is designed to provide high-pressure oil for cooling and lubrication of the N1 and N2 shaft bearings, as well as the accessory drive unit. An oil pump, driven by the accessory drive unit, pressurizes the oil, which is then passed through a filter. The oil is then cooled by an air-oil heat exchanger and a fuel-oil heat exchanger prior to delivery to the engine bearings and accessory drive unit. Scavenge pumps recover the oil, which is then passed through a second filter prior to returning to the engine-mounted oil tank. The engine fuel supply system is designed to provide fuel under high pressure to the engine's combustion chamber. Fuel tank pumps initially pressurize the fuel. Fuel flows through a low-pressure fuel shutoff valve to the engine's low-pressure fuel pump. The low-pressure fuel shutoff valve is commonly referred to as the LP valve and is depicted on the fuel page. The valve is depicted inline green when open and crossline green when closed. The LP valve is controlled by its respective engine master switch. The FADEC determines when the LP valve opens after the engine master switch is placed to on during an automatic start. For normal engine shutdown, the engine master switch is placed off and the LP valve is promptly closed by the engine's FADEC. After passing through the LP valve, fuel pressure is progressively increased by a two-stage fuel pump driven by the engine's accessory gearbox. The first stage is referred to as the low-pressure pump. From this pump, fuel flows through a fuel oil heat exchanger. Here the fuel temperature is warmed by hot engine oil. Next, prior to reaching the second stage, the fuel is once again filtered. In the event the filter becomes clogged, fuel flow will bypass the filter. This will cause the display "clogged" to appear on the engine page. An ECAM message will also appear. The second stage, or high-pressure pump, is where fuel pressure is increased to meet engine operating requirements. After fuel is pressurized by the engine-driven two-stage pump, it enters the fuel metering unit, or FMU. Based on FADEC commands, the FMU controls fuel flow by adjusting the position of the fuel metering valve. Fuel then flows to the fuel nozzles through a high-pressure valve, referred to as an HP valve. The HP valve serves as a fuel shutoff valve and is automatically controlled by the FADEC. During engine start, when the engine master switch is placed to on, FADEC determines when the HMU will open the HP valve. In addition to controlling the LP valve, the HP valve is manually controlled by its respective engine master switch. Fuel is used to provide cooling for the Integrated Drive Generators, or IDG's, oil system. At high thrust settings, the demand to keep the generator operating at the proper speed is less than at low thrust settings. As a result, the IDG oil temperature is relatively cool and does not require a great deal of cooling from the fuel. In this case, most of the IDG oil cooling fuel is returned to the main flow and burned in the combustion chamber. At low thrust settings, the demand on the generator is greater, resulting in an increase in IDG oil temperature. When it reaches a threshold temperature, the respective FADEC opens a fuel recirculation valve and routes a fixed amount of the warm fuel back to the wing fuel tanks. If the IDG oil temperature continues to rise, the FADEC will increase the minimum N2 to reduce the strain on the integrated drive. If the IDG oil temperature continues to rise to yet another threshold, the FADEC increases the flow of hot fuel back to the wing fuel tanks in proportion with the rise in temperature. When returning fuel to the tanks, the FADEC also mixes in some cold fuel to ensure the temperature of the returned fuel stays below a maximum temperature threshold. The engine ignition system provides for engine starting on the ground and restarting in flight. Each engine's combustion chamber is equipped with two identical igniters. These igniters are referred to as the A igniter and the B igniter. Each igniter is capable of continuous ignition operation. The FADEC controls the igniters for all engine start and restart cycles. FADEC uses a single igniter for automatic ground starts and alternates the two igniters for each start. During an automatic engine start, the active igniter is indicated near the start valve indication by the letter A or B. During manual starts, AB is displayed for ignition on the engine page to show that both igniters are in use. FADEC also automatically activates both igniters if engine anti-ice is selected on, ignition delay is detected during an automatic ground start, the engine interface unit fails, or an engine flameout is sensed. Once the engines are started, the engine mode selector is placed in the norm position. When the engine mode selector is returned to the ignition start position after the engines are started, FADEC will activate both igniters on each engine for continuous ignition. Whenever continuous ignition is activated, an ignition memo is displayed. The engine starter system consists of a pneumatically powered turbine starter motor and an electrically controlled start valve. The starter motor is directly connected to the engine's N2 rotor shaft. Start valve opening and closing is normally controlled by the FADEC. The starter is normally used for all ground starts, but it can be used for in-flight starts as well. The start valve is electrically controlled by the FADEC and requires pneumatic air pressure to operate. The status of each engine start valve is displayed on the engine page. Available air pressure for each starter is also displayed adjacent to the valve depiction. During an automatic ground start, the FADEC commands the valve to open when the engine master switch is placed to on. Notice the engine start valve open and the engine begin to rotate. Ignition begins automatically. As the N2 speed increases, fuel is introduced and engine light-off occurs. At approximately 43% N2, the start valve closes and ignition is automatically removed. The start is complete when the highlight around the N2 indication is removed. The start valve indications are automatically removed when both engines are above idle or the engine mode selector is returned to the norm position. If pneumatic air pressure is not sufficient for engine start, the valve will not open, and an ECAM failure message, engine start valve fault, will appear. In the event the start valve electrically malfunctions, the valve can be manually operated by maintenance personnel. Due to extreme operating temperatures, starter engagement time is limited. Engine starter limitations are expressed in terms of cycles. A cycle is defined as the period of time the starter is engaged by the FADEC in attempting to start or to dry crank the engine. There can be a maximum of 3 consecutive start cycles of the engine. Each cycle can last up to 2 minutes, followed by a 20-second cooling period before the starter is engaged again. After the third cycle, a period of 15 minutes must be allowed for cooling. The FADEC has 3 idle modes: modulated idle, approach idle, and reverse idle. FADEC selects an idle mode based on phase of flight and aircraft configuration. Modulated idle can be active on the ground as well as in flight. On the ground, modulated idle is active provided reverse thrust has not been selected. In flight, modulated idle is active while the slats and flaps are retracted. When modulated idle is active, the minimum idle varies and depends on factors such as bleed system demand and IDG oil temperature. For example, the air conditioning system's zone regulator can communicate with the FADEC if bleed demands are not being met, resulting in an increase in idle speed. IDG cooling requirements during taxi can also cause FADEC to automatically increase idle RPM. Approach idle maintains an EPR that is slightly higher than modulated idle depending on ambient conditions. It is active when flaps or slats are extended during flight. Although the increase in idle speed is minimal, approach idle significantly reduces the time it takes the engine to accelerate from idle to go-around thrust. Should the aircraft lose the ability to determine if it is in flight or on the ground, FADEC will default to approach idle as a safety precaution. The loss of both landing gear control interface units, LGCIUs, is one such example. In such an event, approach idle only appears on the ECAM status page. Reverse idle is active on the ground when the thrust levers are placed in the reverse idle position. Reverse idle RPM is slightly higher than modulated idle RPM. The thrust reverser system is designed to assist in slowing the aircraft upon landing and thus reduce the amount of energy expended by the braking system. A translating sleeve moves rearward, enabling mechanical blocker doors to direct fan air forward. Engine core air is not reversed. Full deployment takes approximately 2 seconds. The green hydraulic system powers the blocker doors for Engine 1, and the yellow system powers Engine 2 blocker doors. Reverse thrust is initiated by placing the engine thrust reversers in the reverse thrust range. When in reverse thrust, FADEC continues to provide N1 and N2 RPM overspeed protection. Under normal conditions, reverse thrust should not be used below 70 knots. Reverse thrust is not authorized for powering back the aircraft. A reverser latching lever cannot be raised until the corresponding thrust lever is positioned at the forward idle stop. In order for the thrust levers to move to this position, the reverser latching levers must first be raised upwards. When the reverser latching levers are raised, this allows the thrust levers to be positioned into the reverse range. Reverse thrust is selected by moving the reverse latching levers rearward to reverse idle position. When initially placed in the reverse thrust range, FADEC commands reverse idle thrust. The amount of reverse thrust is progressively increased as the thrust lever is moved further aft. Although maximum reverse thrust can be immediately selected, FADEC will not permit engine thrust to increase beyond reverse idle until all blocker doors are fully open and locked. Full reverse thrust is significantly less than maximum forward thrust for the same ambient conditions. FADEC will not allow the translating sleeves to deploy unless it is safe and appropriate to do so. First, FADEC verifies that the engine is running and hydraulic pressure is available. Next, each FADEC receives positional data from the LGCIUs, which confirm that the aircraft is on the ground. Finally, the thrust lever position is confirmed by at least one spoiler elevator computer, or SEC. As the sleeves transition to the fully open position, REV appears in amber. Once the sleeves are fully open and locked, the FADEC permits the increase of engine thrust and the REV indication changes to green. When reverse thrust is no longer desired, the thrust levers must be moved forward to the idle thrust stop, at which time the sleeves are commanded to close. When the sleeves are sensed to be closed and locked, the REV indication is removed. Should one or more sleeves become unlocked on the ground or in flight, The ECAM message, engine 1 or 2 reverse unlocked, appears, and an amber rev indication flashes momentarily and then remains steady. That is incorrect. 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 That is correct. That is correct. That is incorrect. That is correct. That is incorrect. That is incorrect. That is incorrect. That is incorrect.